Hello and welcome to the last theoretical video of the Python Basics course. This video is going to be about recursive functions. Now, the knowledge that you're going to gain from this video is not specific to Python. It can be applied to any programming language that I know of. And just to keep this course complete, I've decided to include a video about recursive functions as well. Now, what is a recursive function? By definition, a recursive function is a function that calls itself in its definition. What do I mean by that? Well, every function starts with the input by the user, all right? So you're given the input to the function. Now, the function in normal functions makes an output, right? But in the case of a recursive function, the function either makes an output directly or it calls itself with other, in most cases, smaller inputs. And that second function call can also call itself, and so on. So you could imagine that this should look like a loop, right? This will be like a loop. This will have the functionality of a loop. And the truth is that every recursive function can be rewritten with loops, and every loop can be rewritten using recursion. Now keep in mind that every recursive function should make an output from an input in some cases. Right? A function that doesn't do that would, of course, result in an infinite loop. Now, what do recursive functions look like in Python? Well, they look like any other function. You just say def, your function name, your inputs, and then you make a condition for giving the normal output, all right, without the recursion. And then some lines later, you could do something in between. And some lines later, you should say that this is the recursion part, right? Like what should happen in the recursion, all right? And in this steps in the middle, you could, for example, calculate your new arguments for the recursion. Now, to understand recursion better, let's take a look at an example. Let's say we want to calculate the numbers of the Fibonacci sequence. Now, as you know, the Fibonacci sequence is as follows. The first two numbers are given. They're both 1, all right? So the first number is 1. The second number is also 1, and every number after that in the sequence is calculated by adding the two last numbers in the sequence. For example, this 2 is calculated by adding 1 and 1. The two last numbers of it together, add them up, it'll result in 2. And this 3 is calculated by adding this 2 and this 1. And now this 5 is calculated by adding up 2 and 3, of course, and so on. So as a rule of thumb, we could say that every number n, all right, the nth number in the sequence is calculated by adding the n minus 1th number in the sequence and n minus 2th number in the sequence, where, of course, the first number is 1 and the second number is also 1. All right, this is actually all the knowledge that we need about this sequence to make this a recursive function. Now, the way that we could do that in Python will look like this. Would say, of course, our function definition, I've called it Fibonacci here, and we're given our one argument that is the n, that is like saying which number of the Fibonacci sequence we want to be calculated. All right, so if we say 5, we want the 5th Fibonacci number. Now, the main case, this is where we make our normal return, or where we give our answer without any kind of recursion. That's, of course, when n is 1 or n is 2. So if we want to just calculate the first number or the second number, we just return a 1. All right, because those are the two that don't rely on other numbers. Now, in every other case, if n is not 1 or 2, we would return the Fibonacci of n minus 2, and we'll calculate that, and then we'll calculate the Fibonacci of n minus 1, and then we'll just add those up together and return that. Now, to just keep things complete, I've also added another condition here for n smaller than 1. And in that case, I'll just return a 0 because, well, there is no 0th number in the Fibonacci sequence unless you go 0 based. Or there's no 1 minus 1th number in the Fibonacci sequence. So just for every n smaller than 1, I'll just return a 0 just to keep things complete, just to make this function work for every single argument. Now, to understand this code and understand how exactly recursion works in the background, let's trace our code. So I've rewritten the code here. And let's say we want to calculate the Fibonacci of 4. So we want the 4th Fibonacci number calculated. Now let's see what happens in code. All right, when I call Fibonacci of 4, this function will be called, and this entire process will be gone through. Now, what happens at first? It'll say, well, is n smaller than 1? No, so this won't happen. Is n equal to 1 or equal to 2? No, it's 4. So this won't happen either. So what will happen is going to be this. All right, it's going to be this return statement right here. So it'll call Fibonacci of n minus 2 at first. All right, it'll call Fibonacci of n minus 2. That's 4 minus 2 is Fibonacci of 2. This will happen. Now in Fibonacci of 2, it'll see again, this entire process will happen all over again for Fibonacci of 2. It'll say, is n smaller than 1? No. Is n equal to 1 or 2? Yes. N is 2, so it'll return a 1. Who will it be returned to? To whoever called it. All right? Fibonacci of 4 was the one who called Fibonacci of 2, so it'll just return a 1 to the Fibonacci of 4. All right? And this one will be stored right here, let's say. All right? It's exactly at this place, at this line right here. Let's say it'll keep it here. And then this Fibonacci of 4 will go ahead and of course call the Fibonacci of n minus 1, which will be the Fibonacci of 3. And now the entire process will happen for Fibonacci of 3. Is it smaller than 1? No. Is it equal to 1 or 2? No. So again, this will happen for Fibonacci of 3. All right. So Fibonacci of 3 will call n minus 2. Fibonacci of n minus 2. That's 3 minus 2. It's 1. And Fibonacci of 1, you could imagine this case will happen right here. And I'll return a 1 here. And this 1 will be stored right here. And this Fibonacci of 3 will then call Fibonacci of 2. It'll also return a 1. And now those two ones will be added up together to calculate the entire Fibonacci of 3 result that will result in 2. So the third Fibonacci number is going to be 2, which is true. All right, and now this is going to return, this Fibonacci of 3 is going to return its result, which is 2, to whoever called it. And Fibonacci of 4 was the one who called it. It'll return it. And then it'll add everything up together in Fibonacci of 4 to create the end result, which is the 3. So you can see it's not exactly a simple process what will happen in the background, but at least for the programmer it'll look simple. And you could imagine that it's not very efficient, at least for in the Fibonacci case, to do it this way. You could do it way better with a for loop. Now let's see this in action. All right, so I've created a new project and I've copied the code over from the slides. And this is pretty much the same code. I just renamed the function to Fibonacci recursive. Still, if n is smaller than 1, return 0. If it's 1 or 2, return 1. And otherwise, recurse and say Fibonacci recursive of n minus 1 plus Fibonacci recursive of n minus 2. So this is pretty much the same. Let's see it in action. So for that, I'm going to go ahead and print Fibonacci recursive of, let's say in those slides we had 4. So let's have 4 here. Yeah, the fourth number is 3. That is true. And it works perfectly, right? Let's see, 5. It's 5. That is true. 10, for example. All right, 55. All right, so let's kick it up a notch. Let's say, I don't know, 15. See it? Yeah, 610. Let's say 16. 987. And that works perfectly. Okay? But to actually compare it to the non-recursive approach, let us create another function to compute the Fibonacci numbers just without any kind of recursion, all right? So let's say define, I want to call this one Fibonacci. And I'm not going to say that recursive one is Fibonacci recursive, this one is Fibonacci, okay? And of course for n, first two cases are similar. So I'm going to say if n was smaller than 1, then I'm going to go ahead and return 0. And if n was equal to 1 or n was equal to 2, I want to go ahead and return 1. And otherwise, I actually have to do the computation, and this one should not be recursive. So I'm going to go ahead and store the two last numbers in the sequence. I'm going to call the first last number, all right, so actually the last number before the result, A1. And I'm going to let that be equal to 1 for the beginning. And A2 should be the second last number. And I'm going to call that, I'm going to let that be equal to 1 as well. And then I'm going to also make a variable for the result, okay? Let that be equal to 0 for now, okay? And then I'm going to do the actual computation. In a for loop, I want to say for I in range of, and actually how many times do I have to do my computation? That is, of course, n minus 2 times, because for the first two numbers, we'll stop right here, right? for 1 and 2, for n equal to 1 or 2, will directly return a 1 without any kind of computation, all right? So we'll just do this kind of process n minus 2 times, all right? And I'm gonna, in each time, I want to go ahead and let result be equal to a1 plus a2, all right? And then I'm gonna go ahead and say, let then a1 be equal to the, oh yeah, first off, a2 be equal to a1, all right? So I'm gonna make the first last number into the second last number, and the second last number should become the result up to now every time. And after this has happened for n minus 2 times, we have our final result, all right? And at the end, I'm gonna go ahead and return result, all right? Let's check it to see if it works. For that, I'm gonna go ahead and say print Fibonacci of 4 again. Let's see if it works. Yeah, it gives out 3. Let's see, Fibonacci of 5. So let's try some bigger numbers to actually see that this approach is more efficient than the recursive approach, because in the recursive approach, those recursions happen just too many times, and it really takes up a lot of time for it to compute it. All right, you thought that computers are fast these days and it could do what you want. Well, it's not the case. Let's see it in action. I'm gonna say Fibonacci recursive, and for the argument, I'm gonna give it 50. All right, let's see what happens. All right, as you can see, we have to wait and wait and wait, and no result. Recursions are happening in the background. I don't know how many recursions are allowed in Python 3.8 or whatever I'm using. I don't know. You see, no result. Fibonacci recursive. So that's the recursive approach, all right? All of those are happening. Eventually, you'll have a result after, I don't know, 2 days. But as you can see, it's not efficient. It's taking up a lot of time, and it'll take also a lot of RAM. It'll take up a lot of RAM to do all of those recursions and do the computation. So I want to stop it right here. And as you can see, all of these red lines, because I've stopped it myself. Okay, I just hit the stop myself in the middle of a bunch of recursions. All right. So, and as you can see, it says previous line repeated 35 more times. This return statement. All right, the recursion has happened 35 more times than this. Right. So it's like, I don't know, 37, 38 times has happened already, and there was a lot more to go. Okay, so let's go ahead and try the normal approach without the recursion, Fibonacci of 50, and as you can see, immediate answer. It happens very fast, and I could even go bigger on it. Let's say 1,000. I want to compute the thousandths Fibonacci number. As you can see, it's still immediate answer. So this approach was a lot more efficient for the Fibonacci numbers than the recursion. But yeah, recursion is there, you could use it. And in many cases, actually, it does make sense to use recursion. In many cases, the recursion approach is better. In a lot of sorting algorithms, for example. We'll have those further down in the series. So, as another example, let's go ahead and think about factorials, because those are actually, let's not delete it. Well, let's keep the code there. Let's think about factorials. All right, so factorials are like this. I'm gonna write it right here. Factorials are like this. For example, factorial of the number, I don't know, 5 is equal to 5 times 4 times 3 times 2 times 1. Right, so it's just the multiplication of all the numbers from 1 to that number. Okay, that's what we want to compute right now as another example for recursion. All right, so of course, factorial of n, you could imagine, is equal to factorial of n minus 1, all right, and that times n. Okay, and that's the recursion formula for factorial. And of course, the factorial of 0 is equal to 1. Okay, so with that, we could create a recursive approach for factorial. Let's go ahead and do it. I'm going to say def fact recursive, okay, of n, and that's what I want to compute. And if I say, and I'm going to say if n is smaller than 1, All right, so if it's 0 or even smaller, just return 1. All right. Or actually, let's change it. Let's say if n is smaller than 0, return 0. Okay, for the negative numbers. And let's say if n was equal to 0, then return 1. Well, I don't know, because, you know, the factorial of negative numbers don't exist, right? It doesn't make any sense to do it. Oh, I've set a column here. So, and in all the other cases, we are just going to say return recursive of n minus 1, right? And that times n, and that's it. Okay, that is the entire code for it. As you can see, shorter code for the recursive approach, but it's not that efficient. Let's check it out. Let's see, print fact recursive of, I don't know, factorial of 4, for example. So that's 4 times 3 times 2. All right, 2 times 3 is 6, and 6 times 4 is 24. So let's see. Yeah, 24 is the answer, and that's the factorial of 4. And it'll also work for bigger numbers as well. Not going to check it out, but you can imagine for very big numbers, it's not going to be very efficient. And for this, let's also create a normal function without the recursion. I'm going to call it fact of n. And the way that I'm going to do this is actually slightly different than the Fibonacci thing. I'm going to use the for loop variable for this one. Okay, I'm going to use it. I'm not just going to use it as a counter of how many times I'm going to do my thing. I'm going to use it to calculate this stuff because that's only the one variable that I need. Okay, so I'm going to say factorial of n. Easy. Let's just store a result. Let that be equal to 1. All right. And I'm going to say for I in range of 1 to n plus 1, actually. Why I'm going to do that, I'm going to tell you in a second. And I'm going to go ahead and say, just go ahead and say result equals result times I. All right, and that should do it. Let's see, return result. And let's check it out. Let me see. And let's go ahead and print the factorial of 4. That should result 24, right? Let's see. Yeah, 24 is the answer, so it works correctly. But let's see, for example, for 0, it'll given a 1, I guess. That is true, and that works. And the factorial of negative numbers, we could give out anything because that's not defined in mathematics. Let me see. For 1, that should also, yeah, result a 1, and for 2, that should result a 2. Yeah, so it's working perfectly. And let's see, factorial of 100, for example. You can see immediate answer, even though it's a very big number to compute, but immediate answer. And imagine what would happen if I want to do that recursively. I want to say recursive of 100. Let's see. Wow, it worked. It worked with the recursion as well. So let's kick it up a notch. Let's say because you can imagine, you might ask yourself, why did it work in this case and not in the Fibonacci case? Because in the Fibonacci case, we're having 2 recursions for each call. But in the factorial, we only have 1 recursion. We call ourselves once, so to speak. Okay, so let's kick it up a notch. 1,000. Wow. And that's actually a beautiful thing that has happened here. Maximum recursion depth exceeded in comparison. All right, so it can't do it anymore. You know, it just don't want to do it anymore. You know, it just want to, you know, there's just too many recursions happening. All right, for 1,000. But let's do it non-recursive for 1,000. See, immediate answer, right? Big number. Big number here, right here. Immediate answer for that. Okay, so there you have it, and that's it for the code. At the end of the video, I want to leave you with this. The recursive approach should only be used if it makes sense from a time and space complexity point of view. Now, with time and space complexity, I don't mean the space-time from physics. I mean the time the computer will need to compute your instruction, or the space that it will need in the RAM and that should be efficient. All right. In many cases, that is the case, and the best way to do it is recursion. But in the examples that we've seen right now, it's better to do them without recursion. And in the next video, we'll see an example where it's absolutely necessary to do the task with recursion if you don't want to get any headaches in the process of making the program. But that's it for this video, and I hope you enjoyed it. And if you did, share it with your friends and hit that like button and subscribe to the channel for more.